Welcome to Jillian Helms's ePortfolio number 2, problem 2. Steam enters the condenser of a steam power plant at 20 kilopascals and a quality of 95% with a mass flow rate of 20,000 kilograms per hour. It is to be cooled by water from a nearby river by circulating the water through the tubes within the condenser. To prevent thermal pollution, the river water is not allowed to experience a temperature rise above 10 degrees Celsius. If the steam is to leave the condenser as a saturated liquid at 20 kilopascals, determine the mass flow rate of the cooling water required. The givens are stated below. As the steam enters the steam power plant, the pressure is 20 kilopascals, the quality is 95%, and the mass flow rate is 20,000 kilograms per hour. As the steam leaves the steam power plant, the pressure is still 20 kilopascals, but we know that it is a saturated liquid, giving it a quality of 0. As the water enters the steam power plant, the temperature was given as T1. And as the water leaves the power plant, it only rises by 10 degrees Celsius. What we are trying to find in this problem is the mass flow rate of water in kilograms per second. I have indicated on this drawing that the Q in is traveling from the steam to the water. We know that this steam power plant is an open system, which gives us two equations to work with: the conservation of mass and the conservation of energy. We're starting with steam, so we're starting with position 3 and position 4. For the steam, we can eliminate some of the terms in the conservation of energy. We can eliminate potential and kinetic. We can also eliminate work in and work out. And we can eliminate Q in, because we know there's only Q out since the steam is being cooled. What we are left with is m dot H3 equaling to Q dot out plus m dot H4. Manipulating this equation, we get Q dot out equals to m dot H3 minus H4. From here, we need to find our H3 and H4 values. We go to table A4 to find these. H3 requires using the quality given, and it is found to be 2,491.05 kilojoules per kilogram. H4 is known to be the HF value from table A5 since the quality is 0. We plug these values into our equation and we end up with Q dot out equals to 20,000 kilograms per hour over 3,600 seconds multiplied by our H values. We end up with Q dot out equals to 12,442.2 kilojoules per second, and this is for the steam. We also know that Q dot out of the steam equals the Q dot in of the water. Here we have our mass balance and our energy balance for the water. We know that there is no work in, no kinetic and no potential energies, no Q out, and no work out. And again, no kinetic and no potentials. We are left with Q dot in plus m dot H1 equals m dot H2. This is rearranged as Q dot in equals to m dot multiplied by H2 minus H1. We're searching for m dot, so we manipulate the equation again and find that it equals Q dot in over delta H. We also know that delta H equals Cp delta T. We use 4.18 as our Cp value. Since the change in temperature is so minor, Cp will remain constant. We plug these values into our m dot equation and end up with a final answer of 297.665 kilograms per second.